In this video, we are going to discuss canonical form of elliptic PDE. Before going to that, we will define analyticity of a two-variable function. Definition: let D be a planar domain, a function f from D to R said to be real analytic in D if for each x0 y0 in D we have a convergent power series expansion f of xy equal to summation k runs from 0 to infinity, summation j runs from 1 to k, ai k minus j into x minus x0 all raised to j into y minus y0 k minus j, valid in some neighborhood n of x0 y0. Consider a planar domain D. Planar domain means a domain in xy plane. Suppose we have a function f from D to R. The condition for f said to be a real analytic in D is for each x0 y0 in D, for each point x0 y0 in D, there exists a neighborhood n of x0 y0 such that the power series summation k runs from 0 to infinity, summation j runs from 1 to k, ai k minus j into x minus x0 all raised to j, y minus y0 all raised to k minus j converges to f of xy. Then we can say f is real analytic in D. Now we can start a discussion on the topic canonical form of elliptic equations. In the previous video, we have already defined canonical form of elliptic equations. Now we are going to discuss a theorem. The theorem tells us a condition, a sufficient condition for converting elliptic equation into its canonical form. Theorem: suppose LU equal to AUXX plus 2BUXY plus CUYY plus DUX plus EUY plus FU equal to G is elliptic in a planar domain D. Assume that the coefficients A, B and C are real analytic in D. Then there exists a coordinate system zeta eta in which the equation has the canonical form W zeta zeta plus W eta eta plus L1 of W equal to G of zeta eta, where L1 is a first order linear operator and G is a function which depends on 1. Suppose we have a second order linear PDE which is elliptic in a domain D. The theorem gives us a sufficient condition for the existence of a coordinate system zeta eta in which the equation we are considering has its canonical form. The condition is functions a, b and c, which are coefficients of uxx, uxy and uyy, should be real analytic in D. Now we can move on to the proof of the theorem. Let LU equal to AUXX plus 2BUXY plus CUYY plus DUX plus EUY plus FU equal to G is elliptic in a domain D. Now assume the condition functions A, B and C are real analytic functions in D. Since the equation we are considering is an elliptic equation, we will get B square minus AC, the discriminant, less than 0. That is AC minus B square will be greater than 0. Without loss of generality, assume that the function A not equal to 0 for all points in D. We know what is the canonical form of an elliptic PDE. Canonical form of elliptic PDE is W zeta zeta plus W eta eta plus L1 of W equal to 0. Number this equation as 2. So we have to find a coordinate system in which equation 1 has the form 2. Now consider equation number 2. Suppose that coefficient of W zeta zeta is A zeta eta and coefficient of W zeta eta is B of zeta eta and coefficient of W eta eta is C of zeta eta. Now observe that in equation 2, both a and c are equal to 1. That is, in equation number 2, a will be equal to c and b will be equal to 0. So to find the required coordinate system, we have to find a non-singular transformation such that a of zeta eta equal to c of zeta eta and b of zeta eta equal to 0. So we can write that. We have already obtained expressions for a, b and c in the proof of the lemma we are discussed in the topic change of coordinates. A of zeta eta is equal to a zeta x square plus 2b zeta x zeta y plus c zeta y square, and b of zeta eta is a zeta x eta x plus b into zeta x eta y plus zeta y eta x plus c into zeta y eta y, and c will be equal to a eta x square plus 2b eta x eta y plus c eta y square. So we have to find a non-singular transformation such that a zeta x square plus 2b zeta x zeta y plus c zeta y square is equal to a eta x square plus 2b eta x eta y plus c eta y square, and a zeta x eta x plus b into zeta x eta y plus zeta y eta x plus c into zeta y eta y equal to 0. Number these equations as 3 and 4. Equations 3 and 4 form a system of first order non-linear equation. That is, we have got a system of first order non-linear equation to find the required coordinate system. Okay, so we will solve equation 3 and 4 together. But here the difficulty is both the equations 3 and 4 are coupled. Coupled means in the both equations there are derivatives of zeta and eta. To overcome this difficulty, we use the ideas of complex plane and analyticity of functions. For that, consider equation number 3. Now take all the terms in the right side of the equation 3 to the left side. Then we will get a into zeta x square minus eta x square plus 2b into zeta x zeta y minus eta x eta y plus c into eta y square minus eta y square equal to 0, and multiply equation number 4 by the complex number I. Then equation number 4 will become a zeta x I eta x plus b into zeta x I eta y plus zeta y I eta x plus c into eta y I eta y equal to 0, where I is nothing but square root of minus 1. Now define a new function phi equal to zeta plus I eta. Now we claim that the function phi satisfies the partial differential equation a phi x square plus 2b phi x phi y plus c phi y square equal to 0. Suppose this is true, that is phi satisfies phi x square, a phi x square plus 2b phi x phi y plus c phi y square equal to 0. Then by solving this partial differential equation, number this equation as 7. By solving 7, we will get 5, hence we will get zeta and eta. Zeta will be nothing but real part of phi and eta will be imaginary part of phi. So claim a phi x square plus 2b phi x phi y plus c phi y square is equal to 0. We have phi equal to zeta plus I eta. Then phi x will be equal to zeta x plus I eta x, and phi y will be equal to zeta y plus I eta y. Now consider a phi x square plus 2b phi x phi y plus c phi y square equal to, substitute the values of phi x and phi y, we will get a into zeta x plus I eta x whole square plus 2b phi x is zeta x plus I eta x into zeta y plus I eta y plus c into zeta y plus I eta y whole square, which will be equal to a into zeta x plus I eta x whole square is zeta x square minus eta x square plus 2i zeta x eta x plus 2b into zeta x plus I eta x into zeta y plus I eta y is zeta x zeta y minus eta x eta y plus I into zeta x eta y plus zeta y eta x plus c into zeta y plus I eta y whole square, which will be equal to zeta y square minus eta y square plus 2i zeta y eta y. Now by separating real part and imaginary part, we will get a into zeta x square minus eta x square. I have written these two terms from here, and plus 2b into zeta x zeta y minus eta x eta y, these two terms, plus c into zeta y whole square minus eta y whole square, these two terms. Now I have written the real part, and I am going to write the imaginary part. I into this term 2a zeta x eta x plus this term 2b zeta x eta y plus zeta y eta x, and this term plus 2c zeta y eta y. Now observe that in the imaginary part 2 is there in every term, so I can take 2 outside, then we will get like this, which will be equal to 0 plus I 0, because by these two equations, number this equation as 5 and this equation as 6. By 5 real part is 0, and by 6 imaginary part is 0, so we will get 0 plus I 0 by 5 and 6. So we have got 0, hence the claim. So we have got a 5x square plus 2b 5x 5y plus c 5y square equal to 0. This equation can be factorized like this: 1 by a into a 5x plus b plus square root of ac minus b square into 5y into a 5x plus b minus square root of ac minus b square 5y, which will be equal to 0. You can verify this. We have done similar factorization in the case of hyperbolic equations. Okay, you can verify this. From here we will get either this term is 0 or this term is 0. Okay, that is a 5x plus b plus or minus square root of ac minus b square into 5y equal to 0. Number this equation as 8. Now observe that equation number 8 is a first order linear partial differential equation in phi, x and y. So its characteristic equations are given by dx by dt equal to a, dy by dt equal to b plus or minus square root of ac minus b square, and d phi by dt equal to 0. From here we will get phi is a constant on the characteristics, which are the solutions of the equation dy by dx equal to b plus or minus square root of ac minus b square divided by a. We can write that. From the third equation, d phi by dt equal to 0 imply phi is a constant. I call this constant as k. That is, we have got phi is a constant on the characteristics, and the characteristics will be the solutions of first and second equation. Dividing second equation by first equation, we will get dy by dx equal to b plus or minus square root of ac minus b square by a. Okay, therefore we have got phi. Phi is nothing but zeta plus I eta. So we can define zeta as real part of phi and eta as imaginary part of phi. So we have got zeta and eta. To check whether zeta and eta actually gives a non-singular transformation, we have to check Jacobian of zeta and eta. If the Jacobian of zeta and eta not equal to 0 in D, we can conclude that zeta and eta gives the required non-singular transformation. Okay, so we consider Jacobian of zeta and eta. Jacobian of zeta eta will be equal to determinant of zeta x, zeta y, eta x, eta y. Now observe that the function phi we have got is analytic because we got phi from the equation number 8. Here the functions a, b and c are analytic by our assumption. So the solution of 8 will be a analytic function, that is phi is analytic. Then by Cauchy-Riemann equation we will get zeta x equal to eta y and zeta y equal to minus eta x. Substitute that in the Jacobian, we will get zeta x, zeta y. Eta x is nothing but minus zeta y and eta y is nothing but zeta x. Okay, and the determinant will become zeta x whole square plus zeta y whole square, which will be not equal to 0 if zeta x and zeta y not equal to 0. But zeta x and zeta y never become 0 because if possible zeta x and zeta y equal to 0, then by Cauchy-Riemann equation we will get eta y equal to 0 and eta x equal to 0. Therefore we will get zeta is a constant and eta is a constant. That is, we will get phi is a constant function, a complex constant function. But actually phi is not a complex constant function because we have got phi from the equation dy by dx equal to b plus or minus square root of ac minus b square divided by a. Suppose solution of this equation satisfy the equation g of xy equal to c, then phi will be equal to g of xy. G of xy will be a function in x and y, not a constant. So we can conclude that phi is not a constant function. So we have got Jacobian of zeta and eta is not equal to 0 in D. Hence the proof is complete.